EEE 145, Chapter 9, Transformer Protection, Part 2. Okay, so last time we talked about differential protection, mainly to protect against overcurrent. Today, we're going to talk about some other complicating factors of transformer protection that we're going to need additional relay settings to overcome. The three big ones we're going to see is first one, magnetizing inrush, it's called. Inrush. And basically, when a transformer turns on, so you turn on transformer from an inert dead state, you'll have a lot of source side current. Side current. And this is to magnetize the coils. So remember, a transformer is nothing but a giant inductor. And you need to, whenever the inductor is dead, you need to send current in to energize the magnetic field for the transformer. So that's that inrush of current, which is only from the source side. Because the load side, we assume, is dead. There's no source in the load. So there's only one direction where the inrush can come from, and so it's the source side, which has some issues with differential protection because you have an unbound secondary CT current when only one side is sending current to the transformer. So we're going to have to somehow fix or trick the relay to let us magnetize, let the magnetizing inrush in. Otherwise, we'll never get the transformer online because we'll try to turn it on, the inrush will happen, the differential kicks off immediately, and we're just stuck. So we're going to have to figure out something to overcome magnetizing inrush. The next one is going to be overexcitation. We talked about this a few other times, especially for the generator. Same thing here, right? We still have a lot of magnetic coils everywhere. You put voltage on, and if you have too much voltage applied, that's going to have some consequences. And if you remember, it's when you have too much voltage, your magnetic field is too strong, and then you'll run out of the magnets inside the metal core to align, right? Those are called moments. So too much voltage, not enough metal, you can't turn the magnets anymore, and then what ends up happening is you pretty much distort the turns ratio. Right. Once a transformer goes into saturation, or sorry, overexcitation, which turns into saturation, your turns ratio is not constant anymore. So for example, if we put too much voltage and we have overexcitation in the transformer and we increase a current or decrease a current, the secondary side will not have a linear fashion. So you might see some funky things happening. Again, because we're distorting the turns ratio, the differential protection does not like when turn ratio changes, right? So that's another big issue we have to deal with. All right, the last one is called CT saturation. So this is not necessarily the actual transformer itself, but the secondary instrumentation transformer, the current transformer itself can saturate. This is when you have too much burden. Okay, remember, burden is how much impedance we put on the secondary circuit of this CT. When we have increased current, the increased current will cause more burden. And if we either improperly size the burden, or if the CTs are not made perfectly equal, meaning one manufacturer might make it different from others, one CT could go into saturation quicker than another CT, and then you'll get some problems because you'll get incorrect CT readings. Yeah. Again, the differential relay expects the CT readings to be dead accurate. So if one CT goes into saturation and doesn't keep its turns ratio or CT ratio correctly, you're going to create an imbalance in current, and the differential element might trip offline as well. Okay. CT saturation is very prevalent whenever we have very high fault current, because the higher fault currents will cause the CT to saturate quicker. Okay. Now we'll say CT saturation is, you can't avoid it. It's going to eventually happen. When you have fault current in a CT, there's only so many cycles or seconds it could take before it started going to saturation. So it's just something we're gonna have to live with. Again, especially if you have very high current in your system during a fault. So let's go and try to tackle each one by one. Let's talk about the magnetizing inrush for the transformer. So again, when and why does this happen? We're connecting a transformer from a de-energized state. Okay. Now, this is important because you have to, if you take a transformer and you turn it off and turn it back on really quick, it hasn't had enough time to lose its magnetic field, so you won't have this issue. But if you turn off the transformer and wait a couple of hours or 24 hours, then it'll lose its magnetic fields, it'll lose its stored energy, and then you're going to have to do this whole inrush issue when you re-energize the next day. Okay, so connecting transformer de-energized states, and then they say means we need to energize the coils in the transformer, right? Again, we can't get away from this. We have to do it. All right. Why is this a problem for protection? Because we have one side with current, the other side, no current. This is very strange for the differential relay. The 87 will think there is a fault. Okay. Not only is the inrush current only on one side, it tends to be higher than your load current, so it's kind of a double whammy. So here we're gonna have some inrush current coming in from one side, most likely the high voltage side, because that's the source side, and a current going out on the other side is 0 amps. So again, if it wasn't for inrush and those normal operations, you would assume high current on one side, 0 on the other. It's an internal fault, so the 87 would trip. Okay. So the question is, how can we mitigate the impact of inrush current on our protection system? One, we need to detect inrush versus fault current, right? We need to differentiate the difference between these two. Number two, we need to then temporarily block or restrain the 87 element. Okay. So as long as we can detect as inrush, then we can block or restrain the 87 element. And then we'll say if inrush current. Okay. You definitely don't want to do this during a fault, because then you're defeating your whole system. Okay. So that's kind of the roadmap we're going to try to do. So now let's talk about, well, how do we actually do that? How do we program the relay? How does the relay know what is a inrush current? So the big thing with inrush current is there's a DC offset. So if you notice, the waveform is not equal across the zero axis. So typically in an AC system, you'll have a positive half and a negative half, and they're usually equal. But notice that there's kind of like a biasness to a DC component like this, right? And so this is your DC offset. So the peak is much higher, but there's no negative cycle. It's only positive cycle. Okay. Now, how can we mathematically detect DC offset? There's two things that will come up. You'll have second order harmonics, and fourth order harmonics. Without going into much details, harmonics are just characteristics of a system whenever it's distorted. If it's a perfectly sinusoidal waveform, you'll never have harmonics. The more messed up the system is, the more extra harmonics and noise you're going to have in the system. And we can use filters to detect second and fourth order harmonics pretty easily. Anytime you have a DC offset, you're going to have even order harmonics. So second and fourth order harmonics typically don't exist in a power system unless you have a DC offset, which is in this case, the inrush current. I don't think there's any other time in the power systems you're going to see these two harmonics. And so it's a very good indication. If we can detect second order and fourth order harmonics, we know it's inrush. Okay, so what type of relay settings can we use? Well, we can have a second order harmonic restraint. It's typically a setting you'll see in a transformer relay. We can enable this whenever we detect second order. Fourth order harmonic restraint as well. If we detect fourth order harmonics, we should restrain the 87 from operating. Okay, now relay settings wise, Schweitzer Engineering Laboratories SCL recommends that second and fourth order harmonic restraint settings on relays. So restraint settings are equal to 15% full load amps. Okay, so whatever your full load amps is, 15% of that, so 15% of full load amps, that is your restraint setting. Now, one thing to note is during inrush, we're literally disabling our saving protection scheme, the 87 differential. So what happens in the very, very, very rare chance there's a fault in the transformer from the manufacturer, and when we try to inrush, there's a fault. We disable the 87 element, so that's not going to help us. So no matter what you do, always at least have something to save you at all times. So even if we disable all the protective settings in the relay, keep at least one. And we always say keep a 50 element active. Okay. Just in case in that one-off chance there's a fault when we try to disable everything else. So keep a 50 element active as backup. Okay. You should never ever run a transformer naked with no protection at all, because you're gambling on a $3 million device and all. So don't ever do that. Okay, so that's how you protect inrush. Detect inrush, second or fourth order harmonic. You restrain it so we can let the transformer energize and have the 50 element active as a backup. Okay. So next, let's do overexcitation of a transformer. So this, unfortunately, this thing doesn't play. So the idea is the core characteristics is your hysteresis loop. The big thing you need to see here is when you apply too much voltage, you have distorted current. Notice the current is not pure sinusoidal. It's kind of bent a little bit and have spikes everywhere. So that's not good. You're going to cause some problems, especially on the turns ratio coming in and out and the readings on the CT. So again, too much voltage. And somebody will ask, well, what's too much voltage? It's more than the transformer is rated for. If my transformer is rated for 115 kV and I use it for 138 kV system, you might be running into overexcitation. If I use it for a 230 kV system, I'm way, way, way higher than what the transformer is rated. For sure, I'm going to run into some overexcitation problems. Most likely, you're going to damage a transformer. Okay, so too much voltage will cause the core to enter saturation. Because there's no more moments to turn. I mean, that's pretty much what it is. Those little mini magnets, we ran out and it can't hold the magnetic field anymore, or it can't make it any stronger. And so all that, extra voltage we're putting in after saturation, all the extra current flowing in after saturation is not going to get transferred to the other side. So you're going to lose your turns ratio. Why is this a problem for protection? Right? Losing the turns ratio means inaccurate readings. Okay. We have we have unequal turns ratio. Might cause, now it's not guaranteed, it depends how good your CTs are set, but there's a good chance it might cause the 87 relay to trip by accident. Okay. Now, if you're maybe 5%, 10% over the voltage, maybe you might be okay. It probably enter a little bit of saturation, but your 87 relay has that restraint. There's some levels of buffer that it might not trip. But again, if you're like 150% over your voltage, so you have that 115 kV transformer, you're trying to run it on a 169 kV system or some 200 kV system, you're definitely in overexcitation territory, and you're gonna have some problems. Okay. So how do we adapt to overexcitation, right? How can we stop this from damaging the transformer and losing that turns ratio? Okay. Well, first off, remember, overexcitation will lead to non-linear current. Sorry. That's a problem. And remember, anytime we have nonlinear current, what does that mean? Harmonics are present. Right. Now, what can we do? We can look for fifth order harmonics present. If we have a large fifth order harmonic, that's a telltale sign that we have these little spikes everywhere on a current, and then we know we're into saturation region. So if we're into saturation region, what we need to do is we need to make sure we don't trip to 87 immediately and cut customers off. Typically, overexcitation saturation is a gradual thing. It doesn't happen on the flip of a switch, right? It'll be your system is running normally, and then your system is getting a little too hot, a little bit too hot. Maybe some LTCs are operating somewhere, and you slowly creep into it. Okay, it's typically not just an on-off. You go from 100 kV to 200 kV. So if we start entering a saturation region, we don't want to trip the differential immediately, because then we'll lose a bunch of customers. So what we do is we activate a restraint. Right? And this will stop the differential from operating for this temporary over voltage. Most likely we'll send an alarm out to the operator so then they could dial back the voltage, right? And after a certain time, if this doesn't get resolved, then we'll probably trip the circuit. We'll trip the circuit breaker and take the transformer out. Okay. So this is called a fifth harmonic block. And this is typically set to about 35% on the SEL relays. Okay. And so one will ask, well, if we're looking at harmonics, how can we tell the difference between inrush and overexcitation? Well, overexcitation even though the waveform is messed up, it's still symmetrical across the x-axis or across the zero crossing, right? Just look at the blue line, it's symmetrical both left and right. So because it's symmetrical, you won't have second and fourth order harmonics. They'll be absent. Now, you will have fifth order harmonics because the system's all messed up, okay? So that's how we can differentiate inrush versus overexcitation. Inrush is only fourth and second harmonic checking. Overexcitation is only fifth harmonic blocking. Okay. So that kind of pretty much solves the overexcitation issue that would accidentally cause a 87 differential to trip. The next thing that could cause problems for the 87 differential is when the CTs themselves get saturated. So when and why does this happen? You have when fault currents, when high fault currents. High fault currents exist. Basically, you have a pretty strong fault. We will burden the CT too much. Okay, it'll basically start breaking down. Right. And this will cause the CT to become inaccurate. Okay. So basically, this is kind of called a knee curve. We're not going to go into too much detail, but down here, this is the linear region, and you can operate here normally, and everything's fine. This is fine right here in this region, kind of like this much. All of here, pretty much. Anytime you get to the more flatter side, here, this is a saturation region. You don't want to operate here. This is bad. Okay. Anytime this flatter area, so probably about right here, we start entering saturation. This is bad. Don't be here. Okay. Let me put that on the side. Okay, so in the middle, this is a knee curve. You'll hear it one day. Basically, operate below the knee curve, you're fine. Operate above the knee curve, you're in saturation, you're gonna have some issues. Okay. So why is this a problem for protection? We always gotta ask that. If one CT saturates before the other one, which is very common, we will have number one, inaccurate CT information. And then the 87 relay will probably trip. Okay. So again, it's always going down to if we don't feed the relay if we don't feed the 87 relay accurate information from the system, it's going to wig out and trip offline. Okay, so imagine you have a transformer, the high voltage side CT works fine, but then the low side CT doesn't enter saturation too quick, and then we lose information there. Now it's a one-sided current, and now the 87 relay just flips out and trips offline. Okay. This is an issue, especially for external faults where the current rides through our transformer to the next section. We don't want our transformer to trip for our outside fault. Okay. So how do we stop CT saturations from inadvertently triggering the 87 differential? Well, we could use the restraint settings. So remember, we had a restraint settings for the CT mismatch. So this is what they call slope. So slope setting. So slope is very similar to restraint. Right. So restraint setting, they say 15%. Some relays just say a slope of 15%. But a slope is just an X, like literally the y equals mx plus b line of the restraint itself. Okay, so for example, see here with slope settings for CT mismatch. I think SCL relay says SLP1, that's their setting, is equal to 25%. That's what they suggest for their relays. I think GE and other manufacturers, they might say restraint 1, restraint 2, right? But we'll go with SCL because that's where most people use. So the first slope is always for CT mismatch, which we covered on the last class period. Now slope 2, this is more for CT saturation. And the reason why is CT saturation will only, this only happens whenever we have fault current levels. Okay, this x-axis is amps. And so on the lower side of the, before super high fault current, CT mismatch is an ongoing thing. Even in low current levels, you still have CT mismatch. So slope 1 takes care of that. But once you get to the fault current setting, when one CT saturates, we might get past that 25% slope 1 settings, which we don't want to operate because this can be an external fault current. Again, if it's external fault, we don't want this slope to, so we don't want the 87 relay to operate for an external fault. So we need to make sure we have a stronger slope to stop the 87 from tripping. So here we're gonna have a slope 2. This is usually 60% or so. And this is set for CT saturation during external faults. Okay. Note that for an internal fault, the current is going to be so incredibly high that we're going to overcome the 60% anyway. If you remember last time, we did an example problem that an internal fault showed about 16, 20%. I'm sorry, the last class period, an external fault without CT saturation showed maybe a 20% slope, so we were fine. An internal fault, your restraint is over, or sorry, your I operating over I average, that percentage is 200%, which is much higher than 60%, so it would trip anyway. Okay, so coming in our graph, just remember, anytime we're on the top half of this graph right here, this is trip region. Okay. Anytime we're at the bottom half, this is a blocking region. We don't want to trip. We want to restrain. Okay. So big faults typically go at the top of the page above the slope. So you're going to fault anyway. You're going to trip anyway. If it's below, you're going to block. Okay. So just remember slope 1, CT mismatch, slope 2, CT saturation. Okay. And those percentages are pretty common. You usually don't deviate from that. I would say if you want to, if you're deviating away from 25 and 60%, you should have a pretty good compelling reason not to. This is not something that just like, oh, well, let's just do 120% today, right? Because then nothing's going to work. Okay. There's a reason why there's the reason why we have recommended settings. Okay. So let's go ahead and take our 15, 20-minute breaks as we covered a lot. Three topics, very complicated. And so let's do a quick example to kind of rehash the settings and when to use these for which individual phenomenon. So here we got a 87T differential transformer. It's kind of similar to what we did last time, but different relay settings. So number 1, we need to energize the transformer, set the protection scheme to cover this event so the 87 relay does not trip. So what relay settings do we use? What are the values for them? And what is the protection functions we must keep in place as a backup in case there's a fault during inrush? Number 2 is we have to mismatch on the CT selection. We couldn't help it. And we notice that one saturates earlier than the other during faults. Set a differential relay to accommodate for these complications. So here, first off, what is the slope setting or what relay settings do we use to handle CT mismatch? Then what slope or sorry, relay settings do we use for CT saturation and what's the value for that? So pretty simple. Just check out those two. We'll come back in about 15, 20 minutes to see what you've come up with and check your design. So see you guys in a little bit. All right, welcome back. Let's go ahead and check this differential transformer design example we're working on. So here, first thing we say is we need to energize a transformer. So set the protection because remember, energizing transformer, you're basically looking at inrush current. So inrush current is always rich in second and fourth order harmonics. So we could just set in the relay a second order harmonic restraint of 15%, a fourth order harmonic restraint of 15%. This will end up blocking the 87 relay from operating during a inrush event. Okay, and what is the protection function we must keep in place, and what is the settings just in case something goes wrong? We must keep a 50 element in case there's a fault on inrush. And what's a pickup for this 50 element is typically 1000% or 10 times your load current. Okay, because if there's going to be a fault internal to the transformer, it's going to be a really, really high current. It's going to go most likely way above this 1000%. Okay, so that's how you set for inrush. Next thing you want to do is let's talk about some slope settings. So again, remember, we're going to have a problem with CT mismatch, and in case one of them saturates before the others for external faults. So for CT mismatch, we have a slope 1 setting, which is typically about 25%. And after a certain point, a slope 2 setting will come into effect at 60%. And honestly, I forgot to mention this. I don't think you could choose where slope 1 and slope 2 starts. I think that's typically hard coded into the relay itself. Okay. So slope 1 is for lower values of current for CT mismatch. Slope 2 is for higher currents where it'll go into fault current territory and you'll have to overcome a 60% restraint to have the 87 relay operate for a faulted event. But remember that an internal fault will always have a very high percentage here. Typically internal faults are like 200%, 300%, 400%. It's really high, so you should not have any problems with, an internal fault. It's an external fault where you want to make sure that your CT saturation does not trip your transformer for a fault somewhere else. And that's why we need the 60% to make sure that CT saturation doesn't trick the relay into thinking an external fault is actually in an internal fault, and the relay will just basically misoperate. Okay. So that pretty much covers differential protection as a whole, including all the one-off cases we just talked about. But remember our rule of thumb, anytime we have protection, we should have an overall primary protection, which is 87 differential, but we always need a backup protection. And it's always good practice to have a different type of backup protection than the first one. So if we use 87 for primary, it's good to have a non-87 relay as backup, just in case for some fluke, random fluke in the system, the 87 relay is unresponsive. So naturally, we can turn to a overcurrent relay. So when will we need a backup overcurrent relay? When the 87 relay fails to operate, and if it should. Now that could be just the settings were wrong, some CT connection kind of messed up, or we had so many settings like restraint this, restraint that, harmonic this, slope 1, slope 2. There is a chance that you might mess up the settings. I mean, let's be honest, it's a very complicated system. So I'd rather have a tried and true overcurrent backup protection in case those settings got messed up. So it never hurts. So again, 50, a classic 50-51 overcurrent element is always there to protect, is very reliable, and they're pretty much everywhere. So over 50 overcurrent element is the backup protection. Again, in an SEL relay, when you buy a transformer differential, like an SEL 387, it's going to have 87. It's going to have all your restraints. It will have a built-in 5051 overcurrent for you as well. So they're kind of all prepackaged in one box for microprocessor relays. If you're running mechanical relays, you will actually have to have a separate mechanical relay for your overcurrent element. You'll actually need to have 3 because you have 1 for each phases. So if you're running overcurrent, if you're running a transformer protection package with mechanical relays, you're going to have 3 differentials, 1 for A, B, and C phase. You're going to have a minimum of 3 overcurrent relays for A, B, and C phase. You'll probably have a 4th one for the neutral as well. Okay. But just remember, in microprocessor, this is all just one box. But that box has about 500 settings, so you need to know what they all are, or at least the majority of them. So 5051 overcurrent element is our backup, so we're going to focus on that. Now, another event, why we need backup relay, even if the 87 differential will work, what about downstream faults on the feeders? So this is like if a feeder protection fails, right? So remember, we like to have backups of backups. So what backs up a feeder protection? Remember, feeder is a low voltage circuit breaker downstream of the transformer. If that fails, the upstream device is the actual transformer itself, right? So, and so let me say that again. So feeder protection is a low voltage, right? So we'll have a breaker, we'll have our feeders down here. This is a low voltage bus. We will then go to a transformer right here. And we'll probably have a circuit breaker here. We might have a circuit breaker down here, right? There would be some type of 5051 element over here, right? This transformer 5051 element will back up the feeders on the low voltage side because they're more downstream. These are feeders down here, okay? So if the feeder protection fails, the transformer 5051, I think they typically say 5051, acts as a backup protection. Okay. So it's dual functions. This overcurrent protection for transformer protects the transformer itself. It also helps the other feeders and substations as a bonus. Okay, because remember, protection elements and devices, we make a holistic system where every device will cover at least some other device, to where if we look at the substation as a whole, we should have maybe 15 devices where they're all crossing over each other's zones just to give overlapping zones of protections with primary backup systems. Okay. So what device would we use, and how do we design in a protection scheme? So you definitely want, in the STAR, this is pretty much mandatory, you want some type of high side protection. Okay. So typically you have a high side 5051 for relay for the transformer. And honestly, you really should have this. But if you are absolutely cheap and you're somebody does not willing to spend a dime, you can technically use a fuse if you want, but I'm not a big fan of it because once a fuse blows, you have to go replace it. Okay. It's much better if you use a 5051 transformer, but I'm going to put in the parentheses fuse maybe. Okay, I would not suggest it, but I've seen it on the field like this, especially like old designs. Optional, but highly recommended, is a, let me write down here, 5051 for the low voltage side. So some utilities don't have the one cheap out, some do, but you really should have that 5051 on the low side of the transformer because that's the relay that protects the feeders. Okay, so ideally you should have one on both sides of the transformer. If you got cut corners, just put it on the high side, but have something on the high side. Okay. Again, if the guy has a fuse, I would try to fight and get him to put a relay instead. Okay, so now we know where our 50-51 elements are going to be. They're going to be somewhere near the transformer. Now let's start talking about how to do coordination, because remember, every time we're doing a 51 element, we always have to talk about time curves, tap settings, and all that good stuff. Okay, so how does it work for a transformer? So the first thing you always do for a transformer is talk about, well, what's the damage curve? What's the limit the transformer itself can take? So notice the transformer has two curves, right? Every equipment should have this damage curve for you. You have a main curve right here. Okay. This is called your thermal curve, and this is the limit of the current before the transformer pretty much burns down. Okay. So the limit before a transformer has permanent damage. And you're either fixing it or replacing it at this point. Definitely, you should never ever get to this curve, and if you do, you're probably buying a new one. There is another curve called mechanical capability called frequent faults. It's kind of this one right here. Like so. Oh, let's try to make it a little bit better. Like that. And you can see it kind of, it's a little bit lower and it stems off the main one. Okay. This is called a kind of temporary fault line where you're going to do partial damage to the transformer. Okay. Now I say partial damage because it will still work, but you put some mechanical stress on it, some heat stress, maybe some windings, kind of the insulation might start cracking earlier. So what you do is at the end of the day, you shorten the lifespan. Right? So some transformers, they can maybe take 5 hits at this point. So if you hit it 3 or 4 times, they'll still operate. But every time you hit it, you're probably chunking off 5 to 10 years of its life. If you hit it 5 times, you killed it, right? So again, it's not the end of the world if you hit it once, but you really shouldn't, to be honest, right? If you do, you're just throwing money away at this point. So if we have a 10 times fault on the base current, how long will it take for the transformer damage curve to start? Well, remember how faults work. So here, we're going to go at 10x, which is right here, 10 times your nominal current. You go up here, and we're going to hit this point right here. This is where we hit the mechanical curve. What's that cross-reference number? It's about right here. So we know that after 2 seconds, we will partially damage. Oh, sorry. Damage the transformer. Okay. So we hit it, it's bad, but let's say no, there's no protective device. We're going to keep on going. The current's still going to stay longer and longer. We're going to go up this page. We're going to eventually hit this point right here. And then this is about right here. So once you hit that green line, that's bad news. And that's about 10 seconds. So nothing happens after 10 seconds, which 10 seconds is a long time, to be honest, right? Something's cooking for 10 seconds is going to have permanent damage. We will have to replace the transformer, meaning it burnt down. Okay, so that's your 2 points you're looking at. You have that 2 seconds. Hey, we hit it. We need to stop right now. And 8 seconds go by, and then boom, the transformer's toast. Okay. Obviously, neither of these things should happen. We need to put protective devices in front of these curves so we never hit this damage curve for a transformer. Okay. So how do we do that? Well, we've been looking at time over current curves for quite a while. Let's kind of remember how to do that. So first off, select the correct curve for the family to go with the transformer. So remember, we have to choose best fit. Choose the best fit curve. I remember you have that inverse, right? Very inverse, extremely inverse, right? There's a family of curves that will mimic the same kind of slope that this transformer has. And that's why they have different types of curves with different transformers, different equipment. So we might end up picking maybe a very inverse curve. Okay, once we pick that, select the correct time dial. Remember, the time dial will move the curve to fit the transformer damage curve. We'll say move the, and let's put right here relay curve, just to make sure we differentiate the difference, the relay curve. So for example, here, let's see if I'm a good artist today. We will have, oh, that's way too wide. We shouldn't be using that. The curve should be something like, that might be a little too small. Something like that. That's not too bad. So that's our curve. And you'll choose a time down the curve. Notice that the curve is lower and to the left, and it barely scrapes by the mechanical capability curve. So we're covering that. Well, we fully covered the thermal capability curve as well. Okay. Here's kind of a image to show you how to choose the correct time dial. So we have these curves that kind of best fit this transformer damage curve right here. Which one should we use? Well, you definitely want to have the curve that could fit both of these red, like the red fork. So I would go ahead and whatever curve this is just good enough. So we can trace it back. This is a number 5 curve. So this is a time dial of 5. So here I would say, let's choose a time dial equal to 5 to cover the both mechanical and the thermal damage curves. Okay. Damage curves. Okay. And yeah, you're pretty much set for the time down. You're coordinated. There'll be other things you need to coordinate with, but typically the overcurrent relay is the transformer overcurrent relay is the one right next to the transformer relay, transformer damage curve. Right. There will be other things you need to coordinate, like circuit downstream devices. So here's a kind of good example. We have a green line, which is a downstream motor contact. So right here, you have the motor itself. That is this big green line, which is typically a typical motor circuit breaker. So a motor circuit breaker has both the protective function and the circuit breaker kind of all smashed in one device. And this is typically a curve for that. You have the little blue solid curve. This is a custom fuse they put right here on the high side of the transformer. You see in this instance, it's a small transformer. They could put a high side fuse here for protection. All right. And then lastly, where is the transformer damage curve? You can see it's right here. Right. So here is a transformer damage curve, and that's a transformer right here protecting. Okay. So you can kind of see the downstream device. So the fuse is with the transformer. So the fuse must be lowered to the left of the transformer damage curve. And then the motor control center is downstream of both of them. So that should be before the fuse and the transformer damage curve. So you can kind of see where we're cascading them to the bottom and to the left of the page. Okay, so that's how you do your curve coordination. But don't forget, we're not done. The other critical part is we always need a tap settings, right? It's a common thing people forget. They don't set the tap setting, and then all that curve coordination won't do anything. Okay. So we did this several times. Let's just go through real quick. How do we do this tap settings for 5051? Remember, whatever the rated load current, you have to figure it out through the transformer. It's always I load equals MVA divided by square root of 3 times KV. The big difference is, depending on your high side or low side, you have different load currents, right? Because low side in the distribution level will be a much higher current than the high side of on the transmission level. So you need to do this twice, one for the high side overcurrent and one for the low side overcurrent, if you have it. So once you find the low current, calculate the secondary current through the CT ratio. So remember, the secondary current is always the low current divided by the CTR, which was hopefully chosen for you, or if you choose the correct one. Then next, you find a pickup value for your 51 relay. So the 51 element pickup value. This is always 150% full load amps. Okay, so this is your, whatever your I secondary is, that's your full load amps. And then lastly, your instantaneous pickup, your 50 pickup, which should be very, very high. This is typically about 1000% full load amps, which is again your I secondary. Okay, so it's kind of just a rehash of how to do overcurrent settings. So that's pretty much all the major settings you have for transformer differential. I think you guys are pretty much set on that part. So with that being said, I want to say thank you for showing up and watching the video. I know it's really complicated. We talked a bunch of harmonics and whatnot, but remember, transformers they have a lot of transient issues, and we need to have a lot of specialized settings and programmings to overcome these transient issues, so we can have a really good differential scheme that will work all the time and not trip for erroneous reasons with all the layers of restraints that we have on top of it. Okay, so thank you for showing up, and I hope you guys have a good week. Catch you later.